So once you finish the conversion in step 3, what you will do is find the solution to z of t. Now remember this. The governing equation that we derived before, this z of t will have also 2 parts of the solution, just like what we did with single degree of freedom system. So what's this? That means you're going to have, first one is homogeneous, z of h of t plus z of p, z sub p of t. You also have 2 components. The first one is homogeneous. The other one is particular. And homogeneous is easy. That means the right-hand side of the governing equation is 0. The particular one here, you have to be careful because this is the solution when that particular degrees of freedom is subjected to what we call modal loading. And the modal loading is usually denoted by pi over mi. So this pi, again, once you finish the conversion, is no longer carries any physical meaning. It's in the modal space. So this is the modal loading and divided by modal mass. So the first one is when the right-hand side becomes 0, and the second term will be when the right-hand side of the equation becomes pi over mi. All right, so this part has no different from what we did with the single degree of freedom system. Is that clear? Is that clear?
Yeah.
All right. And after that, you have to put them together. Now, this putting them together part, you will need to review the examples I provided in lecture note number 4 and lecture note number 5. See how I put these 2 together. I have 2 examples. Excuse me. One is for 3 degrees of freedom. The other is for 4 degrees of freedom. Please make sure you review these examples in my lecture note number 4 and lecture note number 5. So once you found the z, you have to put them together. So the final solution, which is for dynamic displacement, is the summation of vi of x, which we found vi from where? From step 1. Remember, we found vi from eigenvalue analysis. So you already have vi from step 1 times z of t, and this will be zi. So this is for dynamic displacement, or just the displacement vector. Velocity will be the same, or almost the same. The summation of the products between the mole shape vectors and the time derivative of generalized coordinates. So here it's going to be z dot. So once you found the z, certainly you know how to differentiate z of t to get the z dot of t, right? So in the step 4, you already have the expression of z of t differentiate to get this one. Similarly, for the last one, acceleration for the ice mode, it's just going to be I equals 1 to n, or summation of the product between the mode shape vectors and the second order time derivative of generalized coordinates. Right? Now, notice the following here. This is very important to make sure that you understand the connection. The vector property, because here, the left-hand side, we're talking about vector. That means everything here you have, you know that this is not just a value, because for multi-degree of freedom system, you're dealing with a lot of different numbers. Maybe it's 3 different displacement points. Maybe it's a form or a building. You may have even more, maybe hundreds of thousands of degrees of freedom. So that means this U here is not just simply a value, but it's actually U1, U2, all the way to UN, each one of this. So the vector nature is preserved by Moshe vector, this. Just keep in mind that this, the reason why you're going to get a vector from the left-hand side of the equation is because on the right-hand side, the Moshe vector are all vectors. So if you have vectors here, eventually you're going to get a vector out. So that is the connection between these two. Secondly, the time derivative, of course, only acts on generalized coordinates. And this is the beauty of this decomposition, because by doing so, you just have to solve for z, which you can harvest, you can leverage the knowledge we developed from single degree of freedom systems. Okay? Now, and so for this part, the numerical examples, make sure you review my notes, number 4 and number 5. All right, for that, so let's take a break for 5 minutes. All right? Okay, and now we'll move to the second part of today's lecture, that is seismic resistant design. First of all, let's talk about first. There are 2 design codes I'd like to talk about tonight. The first one is UBC. So what is UBC? UBC is what we call the Uniform Building Code. And there's another organization, they also issue design codes. And this is what we call International Building Code. Now, IBC is very closely related to ASCE or SEI. SEI stands for Structural Engineering Institute. Some of you may also be the member to SEI. I'm a member to SEI in this health monitoring subcommittee. So here, I will show you the typical steps in solving or designing structures subjected to seismic load. So that's the purpose today for this lecture. The first one that we're going to consider is the UBC code, released in 1985. And UBC 1985 may be considered one of the classical design codes because it was pretty comprehensive. It involves about more than 30 sub-steps, and it includes 6 major coefficients to account for different characteristics. When you consider the structure is or the bridge is under the impact of seismic loading, or you may consider as ground motion. In the later one we will talk about later, you can see the significant change from UBC 1985 to IBC 2016. And another point I'd like to make here is these codes were developed by practitioners and also by professors like me. Every now and then we meet together, we go to the conference, and we publish research results. If a professor can argue that the coefficient we use in existing design codes is not conservative, and with supported case studies or sufficient data analysis, the committee will take on that issue to improve the performance of the previous codes to develop new codes. And that's how these codes evolve. And just keep in mind that these design codes will not stay stationary. They always change. Why? Because there's other issues. So the reason to drive this code change, like the first one I mentioned, is the first reason is because of the better understanding of structural dynamics. That's reason number 1. Why we change the code over the year. Reason number 2 is because of cost. Because contractors always want to figure out what is the best way to deliver an acceptable project within reasonable cost. And that's how they maintain their profit margin. If there's a way that they can demonstrate that the code can be revised because I need to save money. And saving money also means saving materials. Saving materials also means being environmental. If you have taken concrete materials, you know that the reduction in the use of cement is a way to preserve the environment, because the production of Portland cement corresponds to a significant amount, a significant contribution to the carbon footprint. So the second reason for the evolution of design codes is because of cost. Sometimes because we want to save the money, so we change that. And the third reason why the costs are changing is because of the development of new materials. Like, as you know, that the performance of concrete, or the maximum compressive strength, today we call high strength concrete. But the definition of a high strength concrete in 1986, today was considered normal strength concrete. Because of new materials, we also have to update the codes for that reason. And the fourth reason for us to change this code is usually because of new discoveries. Sometimes, for example, in the 1995 Northridge earthquakes, they realized that the significant horizontal drift or the horizontal displacement can actually lead to breach falls, because there was not enough support, or what you call breach stopping device, to protect the breach girders from drifting away from breach caps and breach piers. And that's how all these highways, they just fall down because of the significant horizontal drift. The same finding was discovered also in Japan, what we call the Kobe earthquake.